Okay, welcome to FluxNet ECN. We are a community more than 200 early career researchers from over 50 countries. What we want to do with this network is connect young scientists, make it easy to ask questions about research, careers, and funding, and help each other out. Through the ECN, early career scientists can build connections with peers and also engage with more experienced researchers in the international flux community. Most recently, we had a great webinar on CO2 flux and GPP-CIF relationship in April. And we also hosted a hands-on workshop on using flux data for land surface modeling in August. So we often host events like this. So stay connected. If you'd like to hear about upcoming events, just join our mailing list from our website. Or follow us on X or Blue Sky, or connect with us on LinkedIn. Yeah. So today's event is being recorded and will be uploaded to the Ameriflux YouTube channel. So you will be able to watch it again later. And please feel free to post your questions in Zoom chat, and then we will address them during the Q&A session after the talk. So, okay, it is my great pleasure to introduce Professor Denis Baldocchi, Distinguished Professor of Biometeorology, Emeritus at the University of California, Berkeley, and Gauss Professor at the Göttingen Academy of Sciences and Humanities. He has published nearly 400 peer-reviewed papers, placing him among the top 0.05% most cited researchers worldwide, and has served in key editorial roles, including editor-in-chief of JGR Biogeosciences. So we are truly honored to have him with us today. Please join me in giving a warm welcome to our speaker, Professor Denis Baldocchi.
Oh, good afternoon, everybody. Really a pleasure to join you here. Let me try and share my screen here. Make sure I can see what I'm thinking about. So, yeah, make sure. So today, right now, it's 5 o'clock in Germany, and so I know everyone's in different spots in the world. So today, we're going to talk about writing and publishing in science, essentially. And this slide is kind of interesting as a very start, because this is on the bottom list of pictures of a lot of famous science writers. And I think people like this, if you don't know their pictures, should be inspirations for you to think about writing in the science topics, essentially. So as we try to communicate, it's always told to tell you what we're going to tell you, then tell you again. So for some of you who may not have time to stay for the whole presentation, these are some of the takeaways. Good writing really involves many extrinsic processes outside of following the rules of grammar. I'm not a good grammar person, and so this talk will have almost nothing to do with good grammar. But it will lead to how we tell stories and how we pull together our science, essentially. And really, the beginning really starts with reading. Reading a lot, read widely, and read critically. It prepares you to be good writers, essentially. This also includes building intellectual capital to inspire and become great, be creative. My position right here in Germany is a good example. I'm learning so much by seeing these visitors coming past us, giving seminars, talking to students, having lunches with each other. So it's really important to go to meetings, talk to peers, take walks, explore ideas, essentially. And then that will prepare you, once you have your data, to do the writing process. And then it really is critical to have a storyboard, be really self-critical about how you organize it, be willing to absorb criticism and with your peers and your mentors, essentially, and be willing to revise and edit, revise and revise and revise. Be honest with you, I've revised this talk already countless times before we even started here as an example here. So let's get into the talk. I will give you a disclaimer. There's no guarantee that my opinions and experiences are the best way to proceed, but it's a one way. And it has done as well, essentially. Our papers are often published without rejection, and they've been well cited. So I'm quite happy with how things have turned out, to be honest with you. So, and again, I've served as editor-in-chief of JGR Biogeosciences for 6 years, and in that experience, I went through almost 1,000 papers essentially. And before that, I was editor of Global Change Biology. And to be honest with you, my perspective was a lot of the papers that we rejected didn't seem to have gone through a lot of revision. I think a lot of people from different countries may not appreciate that. And often they seem like they were single drafts. And so if there's any takeaway from you all on this, be willing to revise and edit and revise. So I've had students, we've gone through up to 20 revisions before we submit it to a paper, essentially. And so that's why it's accepted. I have a lot of empathy for you all. So many of us are from non-native speaking countries. I like to pride myself that I'm an expert in speaking broken English. My grandparents came from Italy and they did not speak a word of English, and they had a third grade education. My parents were just high school educated, so we didn't have a lot of books and fancy language at home, essentially. And consequently, I actually did really poorly on my test scores going to university here. So I learned to write literally by the adage of making sausage. And here's a nice photo of my mom and dad and grandmother and uncles and family friends making sausage. So this is part of the process. So, and as a student, my professors, Norm Rosenberg and Shashi Verma, who wrote well, would send back my draft manuscripts. Back then we had to do it by hand or by typewriter, to be honest with you, and they'd just be covered in ink, red ink. But it was good. I really became a better writer because of it, essentially. And then Norm really stressed to me about reading a lot, and he stressed to read good nonfiction and good prose. And at the time, he pointed me to the famous nonfiction author John McPhee, who's a New Yorker author, essentially. So yeah, this good advice from my mentors, essentially. For some of you who just want to have a takeaway on some maybe writing books, when I took my English course, my remedial English course, we had Strunk and White, The Elements of Style. It's a simple, thin book, but it has really elegant advice on how to have good grammar and write well. And as scientists, our colleague Josh Schimel has written a really nice book recently that I like. I loaned it to somebody and it disappeared from my desk, so I don't know if it is anymore, but I need to get another copy. But it's a really good book. And Josh very clearly writes in his book, and I want this point to come across to all of us. As scientists, we are professional writers. And so we should expect that. And it's part of our job. Otherwise, people don't know what we did. And it's really important to communicate our work. I've learned to say that I like to write. It's fun. I find it to be a creative outlet. And what I really like is it forced me to understand and defend my science better. I can give you a talk, I can present my data, but it's half-baked. When I have to sit down and actually write and make sure point A connects to point B and point C, the logic's there, writing does that. And so I really hope all of you kind of come across this with this better sense, essentially. Since I was asked to talk about writing, I'll be a little provocative and I'll say, don't rely on artificial intelligence. I did edit this earlier. I said, don't use artificial intelligence. And so I thought I'd step back a little bit, but don't rely on it. It does stifle our creativity. I think it inhibits our logical thought process. It robs us of mastering our subject. I think it diminishes us from the satisfaction of a job done, essentially. And you all can think your own reasons. I have some question marks here. And I finally said, if this wasn't true, why else did you ask me to speak? So I'll leave it there. So let's kind of get it more into this idea of writing and science, essentially. storytelling is so important. We want to write something that people will read. And so part of your job is to have this complex data that's raw, that tries to put it into knowledge and information that tells a story. Sometimes the most important story is associated with the extremes of the data, not just the means. And so again, you want to find that's in your data. And I've learned reading so many good and bad papers that the best papers appeal to the curiosity of the reader, essentially. So we want to really always think about what pulls them in to want to read this, essentially. And you just don't want to have a lab report and it's a dull recording of your observations, essentially. So I learned from Paul Jarvis, who is a leading scientist in our field, to read a lot and to read widely. So again, your homework assignment is, what journals do you read? Where do you find the most impactful articles? Which research groups do you admire most and are inspired by? And do you read their papers? And then once you do that, what do they do in their papers and research that's noteworthy, that maybe you want to emulate as you do your own work? But also use bad papers as a guidepost. Don't do what they do. And so it's also, again, being constructive in your thinking of your reading, essentially, to, again, make you a better author, a better scientist, a better scholar. As we do this, you would definitely want to comply with the scientific method and be creative. And this is a fun thing. We're, again, going to meetings. I went to some of the early FluxNet meetings in Huhtila, Finland. In fact, where Ivan Mamarella is here right now visiting us. And one of the lead scientists was Pepe Hari. And Pepe was an older scientist, and he'd get up early for breakfast. And since I was jet lagged, I'd get up for breakfast. And I'd met him many years ago when he came to the US for a IUFRA meeting. We had wonderful conversations. And one time he mentioned that he and his colleagues had written this wonderful little book, a guide dog approach, a methodology for ecology. And I encourage you all to download it and read it. It has some wonderful discussions about the scientific method, the philosophy of science. It's just a nice little handbook to help you be creative and be a better scientist. So I hope these slides can be shared, or you can write these down later on and look them up, essentially. The other thing with the creative process just comes from Darwin, to think and walk. He was noted for having his walking path. And so every day he'd walk and think and walk and think. And I know early in my career, I was at Oak Ridge NOAA laboratory, and Tilden Meyer was my peer and friend. And every day we'd go out for lunch and we'd go for a long walk and we'd talk about lots of ideas. And we're still collaborating and working together. And then for my other colleague, Shankar Rao, he encouraged us to have notebooks and write down as much as we can, do our derivations or theory. And at NOAA, we had these little green hardbound notebooks. I love them. And so many of the derivations I've had early in my career are still handwritten in these notes. And they were really influential in writing many of the papers I wrote, because the ideas were brought out in these notebooks. And again, it gives you some practice of writing, because you're writing for yourself in a simple manner that helps you have the foundation and material that can later on be used in your paper. Again, travel, attend meetings. It's so important. Here's a nice picture from one of the transformative meetings for me. I was in Oak Ridge, and the IFO conference was held in Knoxville, Tennessee. You have to realize before FluxNet, there were very few meetings. And this one was really unique because it brought together forest ecologists, ecosystem ecologists, hydrologists, and micrometeorologists to talk about essentially the breathing of ecosystems. And so at those meetings, you saw modelers, you saw interdisciplinary scientists, biology, micromet, turbulence, et cetera. And it really forced us how to communicate with each other also, essentially. These events short circuit the slow publication process. You meet the movers and shakers, and you also meet the next generation, if you're older like me, of the future scientists. Be honest with you, I've hired or not hired many people over the years by going to meetings and having either good impressions or poor impressions of individuals that interact with you. And so I think, meetings are critical. And what makes these people successful? Many of them just have this innate curiosity, this initiative, this willingness to try and explore. And I hope this can kind of come across in this talk for you here. So we'll get to these tips that I was challenged to write, and it's kind of a little bit of a preamble. When I became editor of AGU, they were very kind, and they said our job wasn't to be sticklers to grammar and rules of proper writing. That could be fixed a little bit later, but our job is to judge whether the paper was new and novel, and was it making a significant advance to the science. And that's when you submit a paper, your referees are doing. Also, they want to know is whether the ideas were defensible, were they logical, and was the organization of the writing good. So this is really kind of the framework that I use when I would judge a paper, read a paper, and comment on a paper, essentially. So tip number one, I think that was the most important one, is just to write clearly. Can you understand this stuff? I know early in my career, I had a few colleagues who were really, really bright, and maybe they're a bit full of themselves, and they would write in such opaque ways just to maybe show that they're smart, that I didn't think was very constructive, essentially. And so I still think it's very important to write clearly. And as you do so, be self-critical of your own writing. And again, I stress, revise, revise, revise. I often revise 10, 15 times, if not more, essentially. And as I did with this talk here. One of the pet peeves of the editor was just this excessive use of arbitrary acronyms. People seem to be just making them up. And if you read across so many disciplines like I do, it's fine that maybe someone has an acronym that's in their subfield, but it doesn't help working across fields. And in the old days, people had acronyms because maybe paper was expensive and there was kind of page limits. It's all digital now. Just write the words out, and it'll make your paper much easier to read, essentially. So I really, really stress that. A storyboard is really, really important. We've mentioned this already. I'm going to skip ahead. I think choosing your topic is really important. My friend Xiao Pau is always admonishing us to be careful and not write what's called an LPU, as he said. I'm trying to use an acronym, at least publishable unit. To be honest with you, it takes as much time to write a paper that's just pedestrian, to be honest with you, as something that might be more engaging and more important. So at the very beginning, pick your topic, be careful, and think about what you really want to write about. As you know, we're all overwhelmed with too many papers, to be honest with you. And so we should write, but there's a limit also. And then Shashi Verma, my professor, always stressed to me, address the so what question. It's not good enough to say I made these measurements and I want to write this up and have another paper. Says no, we should address the so what. Have we answered a question that is worth writing about, essentially? So as we get into the analysis, two of my wiser mentors, John Norman and Bruce Hicks, always talked about confounding effects and autocorrelation. They always warned us about that, essentially. And so be careful. A classic example really is just taking the random number series. And if you start doing the sums, it's a linear relationship. And often, we are kind of guilty of that when we start using things like growing degree days and other things, and we're trying to relate that with other processes. So, we got to be careful about accumulating random numbers in our analyses. And then the other one is that, causation or correlation does not prove correlation. And there's lots of examples of this. Again, I was at a meeting in Ascona, Switzerland this March, and Pierre Gentin gave a wonderful talk. And again, learning from your colleagues. And he stressed this new book, or actually an older book by Judea Pearl on the Book of Why. And Judea Pearl's a very famous computer scientist, but he was really interested in causality and working with machine language. And so I'm in the middle of reading this book, and I think it's another book we should add to our reading list, essentially. One of the most important factors for all of us, and one that I tried to judge for myself, my team, and as an editor, is that extraordinary claims require extraordinary evidence, essentially. And really put that in the back of your mind if you're trying to aim for some high-impact journals, essentially. I refer to a nice paper my group did on methane hotspots. And I have a wonderful former postdoc, Camilo Reyes Sanchez, who's done some really novel work on repeated footprint models to look at hotspots. The problem is we went back to my old field site here in the Delta, and he found this hotspot kind of here with this red rectangle is? Well, I was really concerned because I grew up in this area and exactly where there's a PG&E gas line. And so I was really concerned that this was just a leak from the gas line, essentially. But they did the extra work. Camilo and Arias Ortiz worked really hard to show that it was real, essentially. And so they applied multiple constraints. We had eddy flux measurements before and after the disturbance. And so we saw that the hotspot came after. So it might have been this pushed up dead biomass that was slowly decomposing. They made measurements with chambers and pore water, stable isotopes. They did DNA analysis, et cetera. And at the end of the day, we were convinced that this was a true hotspot, essentially. And I guess the other recommendation is, as environmental scientists, we have problems that have lots of leads and lags and nonlinear, non-Gaussian, multifactorial interactions. And so we really need to get away from just using old-fashioned parametric multilinear regressions. There's a lot of new tools popping out. My former student, Nancy Kang, introduced me to what's called ACE. It's the alternating conditional expectations. My current postdoc, Armand Armadi, is doing a great job with Shapley values and accumulating local effects. Cove Sturban, another postdoc of mine, worked with Ben Riddell, and we got mutual information theory going on. And then Matteo Detto did some really nice work with Granger causality, essentially going back even further, I should add. So there's lots of new tools there. Again, talking to people, working with each other should make us better consumers and interpreters of our data, essentially. Because Wendy and Silver and I teach an ecosystem ecology course, and there's this pet peeve. There's this very famous paper in Science about biodiversity. When we talk about sampling, is how many samples are needed to kind of bias or provide background for our measurements. But I think we often don't think about how large the area of the samples are. And with Flux people, we're working on a big footprint. We're essentially measuring a population of soils and plants. And often the ecologists and soil samplers are mostly just doing sampling. And so we have to think about that and defend it, essentially. I guess my point is, I'll read a paper and it says I have 15 samples. Well, is that good enough? And why did you pick that 15? So I want a better explanation for that, is my major point. And then also you have to think about the errors and uncertainties. I know a lot of my colleagues are interested in some of these questions like nitrous oxide fluxes and methane fluxes and CO2 fluxes from different ecosystems. When the fluxes are tiny, what is our zero detection limit? Often I don't see that, and I think it's important our community acknowledge that and measure that. The big one right now is with methane from trees. The fluxes are very tiny. They are measured maybe well by chambers, but it might be below the detection limit of an eddy covariance system. And Matteo did a wonderful job on this topic. Also, we have to think about our units and not be ambiguous. Often, if we're looking at fluxes of methane, they'll often maybe mention units of grams per meter squared per day. Well, is it grams of carbon? Is it grams of CH4? Be clear, essentially. And that's really the key point here. Finally, we have to get back to good drawings, good clear figures, and really pay attention. You don't want to have too much clutter. You want to have clear axes. As a young student, I read these papers by Joe Barry and Ulrich Bjorkman, and this is just a simple figure of photosynthesis and light and leaf temperature, but very clear. You can see the C4 plant, the C3 plant, and it wasn't over cluttered. And this is still a takeaway I teach in my classes. And then my former postdoc, Patty Okawa, I thought did a wonderful job in the recent paper we did, just looking at photosynthesis and respiration using isotopes and models and machine learning. I kind of like this figure. So these are good examples. I don't have explicit examples for you, but just be careful about your graphics, essentially. And I think the last one is to be a scientist. I know when I was a grad student, my professors had a friendly competition, but John Norman was the modeler and Shashi Verma and Norm Rosenberg were the experimentalists. And they always were kind of friendly arguing back and forth. And I guess I've learned that I should be a scientist. We should be a scientist and use both models and measurements And this gets back to our multiple constraints. If you see this figure from my early work in Oak Ridge, my direct eddy flux measurements at night were showing really tiny respiration numbers. And we were in complex terrain, we were on a tall forest with lots of storage, and you knew the respiration rates had to be bigger than that. And so only when we started then making measurements of the storage terms, maybe some advection terms, and had numbers that started to match what the model expected us to have, did we come up with better budgets for our fluxes. So again, I think this idea of interpreting your data through the eyes and lens of a modeler and experimentalist are good. So I'll wind down, then we can have some discussions. I have some questions for you all, essentially, some philosophical musings. I talked to a lot of my young people. We go to coffee, and it seems like everyone's obsessed with publishing in Nature, Science, and PNAS, and I just don't understand it. We have a lot of good societal journals. I guess my feeling is that an article in Nature or Science might happen once or twice in your career. Not every paper one should be able to do. As a tongue-in-cheek, being snarky, Troy Magny had this posting on Blue Sky. It says, I just published a paper in Nature. It includes all the greatest hits, a sexy title, 400 co-authors, a global map, and a methods section full of mystery. So, think twice, essentially. I also worry about the future of peer review. So many want to publish, and yet so few want to review. Many of my friends who are now editors tell me sometimes they have to ask up to 20 people to review a paper. And so we have to think hard about that. And again, we have this ethical issue of artificial intelligence. So I prefer that my team and myself write thoughtful, thorough papers. I encourage all of us actually to keep writing first author papers throughout our career. It's something I've done, and I do it. I know some groups don't do that, but I think it's been kind of fun, essentially. Yes, and I stress here that maybe one or two worthwhile science papers in your career. So don't expect everyone, essentially. So, and I think that's it. So I think we can stop here. I'd like to hear more from you all, and let's have a nice discussion.